on, please?
So right
Yes,
now
sir.
no recording is
I
there.
No, recording is going on. I can see. Is there no recording going on? Yes. Anurag
Just
Singh.
just now it has started, sir.
Yeah. So there should be only one recording going on, please. Again now, I don't know how many recordings. Hopefully only one recording is going on. Otherwise it unnecessarily takes up space. So good afternoon, everybody. And today we start our discussion on the next module, which is logic and deduction. Before that, I want to inform you that on Monday, 6th September, 8 a.m., we have our first class test. It will be a 1-hour test. It will be a 1-hour test. So logic has been one of the most intriguing topics which has been discussed since a long time. Now I see that there are two, so now one only, good, which has been discussed for a long time. Whether you look at the Indic civilization, the Greek, the Chinese, the Middle East or medieval Europe, you will notice that logic has been going on for a long, long time. Typically, logic, there are 2-3 classes going on simultaneously. I don't know what is happening. Can somebody ensure that there is only one class where people have joined?
Yes, sir. I can check.
So the original aspect of logic started everywhere with geometry, because logic is trying to define a formal set of rules by which we can do reasoning. So this concept of geometry, whether in ancient Egypt or India or or South America or Greek or China, all of them did logic through geometry and calculations. Then in India, there was a very evolved logical paradigm, both under the Nyaya and the Vaisesika philosophy. There was also a method of these 4 levels of argumentation. Then Sanskrit language itself brought in a lot of argumentation. Then there was this Chatushtoki, which was a 4-level argumentation. Later on, Buddhist and Jain systems, and then the formal systems and Vedantic systems. In Greek, it started again with propositions and geometry, and then moved on to the most advanced, the first sort of logic came out through Aristotle's syntax and semantics. In the Middle East, Ibn Sina, which is also known as the Avicennian logic, they introduced concepts like inductive logic. In China, there were many new systems, and they also borrowed the Buddhist systems from India. Eventually, the post-Aristotelian phenomena came into Europe, from where we have our traditional first-order logic. Today, logic is in all forms of description of language, description of mathematics, and we will study primarily propositional and predicate logic. Predicate logic is such that predicate logic is as powerful as computation. We will also not study higher order logic, logic of numbers, computation. Logic has also come in psychology. Logic has come in philosophy. Logic, of all of us know, has come in circuits, in complexity theory. So logic is a very fundamental paradigm of science, and AI has got many aspects of logic where AI logic is used. Today we shall start the basics of our study of logic. That with the propositional logic is what we shall start with. Propositional logic is also the basic form. It is also known as Boolean logic, where we use variables and these variables can take values true or false. Here are some of the examples that we did in our video lecture. The first is, if I am the president, then I am well known. I am the president and I want to prove. So I am given two facts. Fact one, if I am the president, then I am well known. I am given fact two, that I am the president, and I want to prove the goal that I am well known. Is this statement true or false?
True, sir.
True.
True.
So what we do is we model I am the president as a Boolean variable A. And we model I am well known as a Boolean variable B. So I have F1 says A implies B. All of you know what A implies means?
A plus B bar.
Yeah. A implies B is equivalent to not A or B. It also says that if A is true, then B is true. If A is false, I don't know what the value of B will be. So A implies B, its truth table says that A implies B is true. If A implies B is true, then the conditions are that if A is true, B will be true. If A is false, we don't know what will happen. So the truth table of A implies B is defined that way. And my goal is what? My goal is B. So my deduction system says that A implies B and B, this whole thing must imply B. Sorry, A implies B and A. A implies B and A must imply B. So this is what we would like to prove, that A implies B and A, the whole thing together implies B. That means if the left hand side is true, the right hand side will have to be true. This is how we formulate our deduction. Let us come to the second one. Is the second statement true?
No, sir.
It is not necessarily true. That means it is not always true. For example, I say if I am the president, so I am the president, I have coded as A. I am well known, I have coded as B. I am not the president is not A. And I am not well known is not B. I'm trying to prove this formula. I'm trying to set up my formula, which I want to prove. I want to say A implies B and not A implies not B. This is the formula. The formula that I've set up using Boolean logic is A implies B and not A. This whole thing, if the left hand side is true, then not B is true. But this formula may sometimes be true, may sometimes be false. Can you tell me when this formula is not correct or will be false? Give me an example. Give me an example when this formula is false.
Hello.
Yes.
Sir, what if the person is a vice president? So he would also be a well-known.
Vice president is not defined here in this set of statements.
Sir, if the set of
So then you can say that a person is well known. He is Cristiano Ronaldo, so he is well known. You
A
have to
is
prove
false
that
and B is
A is
true.
false and B is true.
So let us look at a situation where we set A equal to false and B equal to true. A equal to false and B equal to true. Then A implies B is true or false?
False.
True.
true.
A implies B is defined as not A or B.
It is true.
So,
Yeah.
so it is true. So this part is true. This part evaluates to true under the assumption. So I get A implies B. This part is true. Is not A true or false?
True.
True. So the whole left hand side is true. So this whole left hand side becomes true. What about the right hand side?
It is false.
It is false. So now I have a situation where left hand side is true and right hand side is false. Therefore, this implication turns out to be true or false?
False.
False. So there is one assignment for which this formula is not true. So I will say that the statement, if I am the president, then I am well known, and I am not the president, this does not lead me to the conclusion that I am not well known. So that means that this formula that I have set up is not a,
Tautology.
not a tautology. This formula that I have set up is not a tautology. Let us take the third one. If Rajat is the president, then Rajat is well known. Yes, Mayank, Sonu, I am sharing something. I am sharing slides. I am writing on the slides. Are you in our group or you are in some other group?
This group only, sir. I
Then
can listen to you, but
no,
I can't.
then you do one thing, you get out and get in again.
Okay, sir.
So so take the third one. If Rajat is the president, then Rajat is well known. Rajat is the president, so Rajat is well known. So if I now model this, Rajat is the president as A, Rajat is well known as B. So my first part is A implies B, the second part is A, and the third part is B. Now you can see that this formula is identical to the formula of the first statement. This formula is identical to the formula of the first statement. That means though the sentences are the same, the formulae are identical. All right. Though the sentences are different, the formulae are identical. So let us see how we set up and prove such things. So in order to do this, we use what is called propositional logic. It is also called zeroth order logic. The only thing we have in zeroth order logic or propositional logic is we have a set of Boolean variables. These Boolean variables can take, in our modeling of propositional logic, we have Boolean variables which can take values true or false. Then we use standard Boolean operators and or not, implies, etc. to code our formula. And these connectors have their standard meaning. defined by their truth tables. Now once we have seen the whole set of sentences on which we have to do our deduction, we first set up what will be find out what Boolean variables we will choose. With phrases will become Boolean variables. Then we start coding the sentences. Once we code the sentences, then we create a combined formula for deduction. And our combined formula is of this form. F1 and F2 and so on and so forth. Fn implies some goal, where F1 is encoded out of one sentence, F2 is encoded out of another sentence, F3 is encoded out of a third sentence, and so on and so forth. And finally, we get the goal. Mayank, Sonu, are you back? Mayank, Sonu is somewhere in some other class.
Yes, sir.
Oh, you're back?
Yes, sir.
Can you see the screen now?
No, sir. Some technical glitch I am figuring out.
Okay. So what we try to do is that we try to formulate a combined formula for our deduction, and we try to prove that this is true under all circumstances. That means we want to prove that this is a tautology. Whatever you say, this is true. That is our method of proving this, ensuring that this deduction works. In our language, this whole concept of tautology is also called the formula is said to be valid. We also say that the formula is said to be valid. And when we talk about each circumstance, then these circumstances are called interpretations. We'll learn all of this slowly. And for Boolean logic, to do that, our simplest way to do that is to form a truth table. Form a truth table out of this combined formula and then prove that it is a tautology or not. So now we start doing whatever we had done earlier. If we look at our first problem, our steps are: we will look at the problem, choose Boolean variables. Then we will decide on the connectors. Then we will code each of the sentences. And then we will make a combined formula of the form F1 and F2 and so on and so forth implies goal. So here once we redo what we had already just seen, I have now coded my Boolean variables as A as I am the president, B as I am well known. I code the sentences, F1 first sentence as A implies B, code the second sentence F2 as A. My goal of deduction is G. The formula I set up is F1 and F2 implies G, which is this, and I want to prove that this formula is a tautology. So in order to prove this formula is a tautology, I will set up the truth table. And what I will do is I will set up my truth table. Suppose this combined formula is called F. Then I will set up my truth table. There are only two variables in my truth table, and I will write down all possible: true, 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 false, false, true, false, false. And this is my combined formula. And I can easily figure out that this combined formula is true under all such circumstances. These circumstances which form the rows of the truth table, that means where I assign my truth table, are known as my interpretations. And we say that a formula is said to be valid. A formula is said to be valid if it is true under all interpretations. A formula is said to be valid if it is true under all interpretations. We will also say that a formula is said to be satisfiable if it is true under at least one interpretation. So a formula is said to be satisfiable if there is at least one interpretation for which it is true. In the case of Boolean logic, there will have to be one row for which it is true. So a formula which is valid is always satisfiable. A formula which is false under all interpretations is said to be unsatisfiable. A formula which is said to be false under all interpretations is said to be unsatisfiable. Okay, so let me ask you a simple question. If a formula is valid, suppose I tell you that a formula A is valid, then not A is what?
Unsatisfiable.
So, right. If A is valid, not A is unsatisfiable. Is that clear to everybody?
Yes, sir.
Yes, sir.
And a formula which is for which there is at least one interpretation for which it is false is said to be non-valid. So there are these four terms: valid if it is true under all interpretations, non-valid if it is false under at least one interpretation, satisfiable if it is true for at least one interpretation, and unsatisfiable if it is false for all interpretations. So these are the four things we will be concerned with. And as we move to more and more advanced logics, the definitions of interpretations will change. But for finite number of Boolean variables, the truth table or the space of all interpretations is finite. But in general, when we go to higher logics, it need not be finite. So let us come to our second example. Our second example was.
Sir, I have a query. Like for the valid, not of valid, it will be like not of all interpretation means some interpretation, like false for some interpretation. So false for some.
If a formula is valid, all right.
Yes.
So it is true for every interpretation.
Yeah. So yeah. Yes. Sir.
So not of A will be what? The outcome will be false, no, for every interpretation.
Yeah, but if we'll make the statement like like not.
It's not about a statement. I give you a Boolean formula A.
Yes.
Now this Boolean formula is made out of 5 variables, 5 Boolean variables. So how many rows are there in the truth table?
2 to the power 5.
So now for every row, the formula A, let us say, so let us call this formula A dashed. So for every row, this formula A dashed will be either true or false.
Yes.
So now what about formula not A dashed? What is the meaning of formula not
Okay.
A dashed?
Okay.
The meaning of formula not A dashed is wherever A dashed is true and not A dashed is false. No, that is the meaning of
Yes.
not.
Yes, sir. Yes, sir.
So now if a formula is true for all interpretations, not A will be false for all interpretations.
Yes, sir. Yes, sir.
Got it?
Yes, sir. Thank you, sir.
So now let us come to the second example. The second example said that if I am the president, then I am well known. I am not the president, so I am not well known. Our same encoding. And once we do the same encoding like we did a little while earlier, I have F1 is A implies B, F2 is not A, G is not B. My formula structure remains the same. F1 and F2 implies G, which is this. And if I set up the truth table, you will see just like you all just told me a little while earlier, I will find one row of the truth table to be evaluating to false. That means there is at least one interpretation for which the formula is false, which means that this formula is not valid. This is not a valid formula. But is it an unsatisfiable formula?
No.
No.
No,
No.
it's satisfiable.
It is satisfiable. It is non-valid. It is satisfiable. But it is not a valid formula. It is not a tautology. Now that Rajat part, if we do the Rajat part, as we have seen, that the first one and the second one identically, their whole identical formula structure is the same. That means they are talking about the same logic. So many times you will see that where the context changes, but the deduction part remains identical. So, but can you do if Asha is elected VP? Tell me what will be the Boolean variables?
Sir, if Asha is elected VP, Asha is A.
Is
A is
Asha?
Asha is elected VP, and the
Asha
next
is
one
elected VP. Okay.
then Rajat is chosen as GSec and
GSEC, General Secretary.
sorry, General Secretary. So
You are
B
not
is
used to IIT parlance.
no, sir, and
These are all hostel and gymkhana.
no, sir. Actually, I haven't been to IIT yet.
Arati is chosen.
So as treasurer. Then next is Rajat is not chosen as GSec.
No. Now I have.
Okay, we have to
There is
write it
no
down.
other
Okay,
Boolean
so
variable required, isn't
no,
it, from this whole thing?
now first we have to write if Asha, if A,
F1
okay, F1, if A arrow, I mean A arrow,
implies, right? Don't
sorry,
write arrow.
A implies B, and
F2
then Bharti is chosen as treasurer.
is this F1? Can
No,
somebody tell me? Is this F1?
no, actually,
C
A implies B and C.
B.
And put your brackets correctly. When you write A implies B and C, put your brackets correctly. What is F? What is the second statement?
Not B.
Not B. And goal?
Not A.
Not A.
Goal is not A. And my method of doing everything is to set up the formula F1 and F2 implies G and prove that F1, F2 implies G is a
Tautology or
we have to check whether F1 and F2 implies G is valid or not. How many rows will the truth table be?
8
8.
2 power 3.
Yeah, it will be 8 rows And what are you expecting to get? What are you expecting to get?
Tautology.
Tautology.
Not tautology.
Not tautology. Okay, all of you do the 8 truth table.
Sir, tautology.
So it says it does not tell you whether A is true or false. It just says A implies B and C, and it also tells you not B. So is there any possible combination of A, B, and C for which this formula becomes false?
All of them are true.
All of them are true. You can work out, you will get all of them are true. The next one is the same ABC. The same ABC. What is F1?
Same.
What is F2?
Just B.
And what is goal?
A.
Is this a tautology? That means is F1 and F2 implies G a tautology?
No.
Or is it valid?
No. Not valid.
Tell me an assignment for which the formula will become evaluate to false.
B is true, but A is false.
So I am setting A equal to false and B equal to true. Sorry, is there no C here? ABC?
C equals to false.
So you're saying A equal to true, A equal to false, B equal to?
C doesn't matter. I mean, C can be true and false.
No, whatever. You tell me. Give me one interpretation.
A false, B true, C false.
Let us look at this interpretation. Under this interpretation, F1 is true or false?
F1 is true.
F1 is true. F2?
True.
It's true.
And G?
False.
So this makes the formula false. Got it? Do the next one. How will you code it? Again, my A, B, C remains the same. A is what? Asha is elected VP. So A is this. Rajat is chosen, GSEC is B. Bharati is chosen, treasurer is C. What is F1?
A implies
A
B or
implies B or C.
A implies B or C. What is F2?
B bar.
What is goal?
A implies C.
Very good. Is this a tautology? Is this valid? That means my whole setup again, my deduction setup is F1 and F2 implies G. Is this a tautology or not?
no, sir.
No?
It's a tautology, sir.
I think it is.
Work it out. Work it out.
No, sir, not a tautology, because if A is true, then maybe B is not, means Bharti is not a treasurer.
No. If you to prove that it is not a tautology, you have to give me at least one combination of A, B, and C for which the formula is false.
A is true, B is true, and C is
false.
A is true,
B is
B
true,
is true,
C is false.
and C is false.
Yes.
Okay. So if A is true and B is true, then F1 is true or false?
So F2 is false, and F1, and F2 will be false. And if the left-hand side
is false, the formula becomes true.
Exactly.
See, if F2 is false, if B is true, you are saying, then F2 is false, right? Have everybody understood? So this formula evaluates to F1 and F2 implies G evaluates to what? F1 and false evaluates to G, which is false evaluates to G. This is always true. So this counter example does not work. This counter example does not work. Any other counter example? To do a proof, you have to make the truth table or symbolically prove it or open it up and simplify the expressions. Otherwise, if it is false, so this formula you check again. Let us do the next one. What does the next one say? What is F1?
A implies not B and C, or B and not C.
Everybody look at it very carefully. This says either or, but not both. Which formula in logic or in circuits?
The XOR function.
It's the exclusive or. It is the exclusive or. So F1 here is exclusive or. What is F2? What is F2?
Not B.
And what is my goal? Correct. A implies C again. Is this F1 and F2 implies G a tautology? Can you tell me whether this is the tautology or not? Work it out quickly.
Yes. No, wait.
No, sir, it need not be a tautology.
So tell me when it is not. Give me an example of when it is not.
So if B is true, then it is always true, and if B is false, F1 evaluates to A implies C. So both are the same, so it is a tautology.
Others, please think, let me know. Anybody else would like to try? Is it a tautology or not? Anybody else? Kirti?
So it is a tautology, sir. Like here we have to consider A should be true because it is given that if Asha is elected. And according to F2,
B definitely has to be true or false. B definitely has to be
false, yes, sir.
false.
A should be true, B should be false. So this implies that C has to be true to satisfy
So
F1.
C has to be true. So if C has to be true, then you have only two options, whether A is true or A is false. If A is false, in any case, again, the formula becomes true. So A is true and C is true. So you're done. So how do we work it out? We get some terms. Our terminology is like this, that a formula, an interpretation of a formula is the assignment of truth values to the Boolean variables. After we assign truth values to each of the Boolean variables, we know exactly what the formula evaluates to. So that is called an interpretation. And as we just discussed, a formula may be valid if it is true under all interpretations. A formula may be non-valid if it is false under at least one interpretation. A formula may be satisfiable if it is true under at least one interpretation. And a formula is unsatisfiable if it is false under all interpretations. Now, verification of validity of a Boolean formula in algorithmic context is known to be NP-hard, which means that till now nobody has found a fast polynomial time algorithm for it. However, the easiest way to do is truth table, but we know that if we have n variables, the size of the truth table may be 2 to the power n. So there are many other ways of solving it quickly. One is known as the tree method. So let us look at any of our formulae. Our F1 and F2 implies G. So let us look at one of them. A implies B or C. A implies B or C. And what was it? Not B implies A implies C. This was our formula. So I can now choose a particular variable. Let us say I choose a variable B, and I can make B equal to true and B equal to false. I know that if I make B equal to false, what happens to the formula? Sorry, if I make B equal to true, what happens to the formula?
Evaluates to true always.
The formula evaluates to true. Now, when I make B equal to false, then what happens to the formula? It becomes A implies
A.
A implies C implies A implies C, right?
Yes, sir.
It becomes A implies C implies A implies C. The left hand side, if you put B equal to false, you can remove B by putting B equal to false, you will get this, and this can easily be seen to be true. So this is called the tree method, by which you need not necessarily really write down the whole truth table. If you appropriately choose the order of the variables, then you can find it. The other very interesting data structure where such Boolean formulae are encoded are known as BDDs, or binary decision diagrams. I will not teach what BDDs are. I would request all of you to just go through BDDs. BDDs are a graph-like structure which was evolved in the early 80s, where you could represent a Boolean formula as a graph structure, and which is ordered by variables. So once you have ordered by variables, the interesting thing about BDDs is ordered BDDs are canonical under the same ordering, which means that if I give you two formulae whose syntax may be looking different, but they are actually identical formulae, then one way of making the formulae identical is to draw up the truth table or write them down in sum of products form, both of them, or write them both of them down in product of sums form. The BDDs are such that if two formulae are identical, then for the same ordering of variables, the BDDs will be identical. But I will not do BDDs because that is not part of what we want to do here. The other ways of deduction, other way of proving it is by natural deduction. Natural deduction uses rules of logic. That means there are these rules of logic, like you have rules in axioms of logic, like you have axioms of probability. So you have a set of rules like modus ponens, which says that if some sub-formula A implies some sub-formula B is there and A is there, therefore you can remove this and replace it by B. Then there is modus tollens, which says if A implies B is true and not B is true, then not A is true. So there are these sets of formulae which are complete. That means if you use these, then any form of deduction can happen. Like you do symbolic, simplification, like you do Bodmas rule and all that. Similarly, there is a theory in Boolean logic called natural deduction. Now, a method, any method, has got these two properties. So given a formula F, we want to know whether it is valid or satisfiable. Suppose we want to know whether a formula is valid or not. So we want an algorithm. Now, an algorithm is said to be sound when, if the algorithm says the formula is valid, then the formula is valid. So it is one side of the if implication. That means if the algorithm says the formula is valid, then the algorithm is correct to the sense that the formula is always valid. A formula is said to be, and a method is said to be complete if the other way around is also true. That means if the formula is valid, then the method will prove it to be valid. So it is an if and only if the method can be sound or complete. And we will discuss this in more detail when we come to more complicated situations. So a method can be sound and complete. A method is said to be sound if the method proves something to be true, then it is true. A method is said to be complete when, if it is true, the method will prove it to be true. So these are certain terms that we want to know. But Boolean logic is not sufficient. Why is it not sufficient? Look at these sentences that we have. Wherever Mary goes, so does the lamb. Mary goes to school, so the lamb goes to school. Now, if we try to encode this in Boolean logic, then obviously Mary goes to school, we can encode as A. Lamb goes to school, we can encode as B. But this idea of wherever, this part which talks about wherever, this opens up infinite possibilities because I don't know where Mary can go. If I knew where Mary can go, then I could, if it was finite, I could list it out that for each of them I could list out a Boolean variable. Similarly, for each of those places, I could list out a Boolean variable for lamb goes there. But if it is only written wherever, this opens up an infinite set. And because it becomes infinite, therefore, Boolean logic is by a finite set of variables is not sufficient. Look at the second one. The second one says no contractors are dependable. Some engineers are contractors. Therefore, some engineers are not dependable. So it becomes difficult to model each of this. Look at the third one. All dancers are graceful. Aisha is a student. Aisha is a student can be modeled as a proposition, as a propositional variable. Aisha is a dancer, that is also can be done. But the first one, all dancers are graceful and some student is graceful. Both of these will find difficulty in modeling it in Boolean format. So every passenger is either in the first class or in the second class. Each passenger is in the second class if and only if he or she is not wealthy. Some passengers are wealthy. Not all passengers are wealthy. Therefore, some passengers are in the second class. So as we go around more and more complicated logical connections and arguments, we will see that Boolean logic is not sufficient. However, we will also see that Boolean logic is very powerful in modeling even very, very complicated situations. For example, I'm just showing you another simple example. And we will work out on these examples in the next day. The example says, if the unicorn is mythical, then it is immortal. But if it is not mythical, then it is a mortal mammal. If the unicorn is either immortal or a mammal, then it is horned. That means it has horns. The unicorn is magical if it is horned. Now I want to conclude, is the unicorn mythical? Is the unicorn magical? Is the unicorn horned? Tell me which answer you think is correct.
So the truth value of unicorn being magical is not known from the previous two statements at all. So how do we know whether
Tell me which of them is confirmed to be true and which is confirmed to be false and which could be true, could be false.
So I think being horned is confirmed to be true because if the unicorn is either immortal or a mammal, it is horned. And the unicorn is immortal if it's mythical, but if it's not mythical, it is definitely a mammal. So considering all cases, it seems like horned will be true.
And the others?
Still thinking, sir.
To be true, because if horned is true, then the unicorn is magical.
So if you can prove that horned is true, then magical will become true, no?
yes.
But
Only,
it may not be. But it may not be mythical.
Yeah. So let us see what are my Boolean variables? What are my Boolean variables? A.
Unicorn is mythical.
Mythical. B.
It is immortal.
Mortal. C.
Mortal. Sorry, a mammal. Mortal mammal.
Mammal.
Yes, mammal.
D.
Yes. Horned.
Horned. E.
Magical.
So is everybody convinced that these are the 5 variables that are required? These are the 5 variables that are required. Is everybody convinced?
Yes, sir.
Mortal and
So,
mammal. Mortal and mammal both are same.
Mortal and mammal are same. Who told you?
So in the first statement it is written then it is a mortal mammal.
So it will be mortal and mammal. No? Mortal and mammal is the same. It did not tell you. No?
Okay, sir.
What is F1?
A implies negation of B.
Then?
But if it is not mythical, and if negation of A implies
B and C.
Yeah, B. Yeah, B and C.
Correct. Everybody is okay with this?
No, sir. The brackets position is at the starting and up to negation 8.
No. It says if the unicorn is mythical, then it is immortal. But if it is not mythical, then it is. How can the bracket become up to something else? A implies not B is very clear, right? This statement.
Yes, sir. Yes, sir.
Have you understood now?
Yes, sir.
What about F2?
Negation of B or C
C implies D.
Not B
Or C.
Or
C.
Not C. Or C or not C. Oh, C.
C. It's magical. Sorry, mammal. Sorry, and mammal is given.
Implies?
Implies horned. So horned is D.
What is F3?
D implies D.
E implies D.
D implies E.
D implies E or E implies D? D implies E or E implies
D
E?
implies E.
D implies E.
D implies E.
Correct. Now I have G1 is A. G2 is
E.
And G3 is
D.
And now you have to prove F1 and F2 and F3 implies G1 or not. F1 and F2 and F3 implies G2 or not. And F1 and F2 and F3 implies G3 or not. So do that as an exercise. We'll stop here today. You can stop the recording. If anybody has any questions, we'll answer.